I'm ready whenever you are.
Okay, what I wanted to do is to start to go over some of the electrochem, just because I don't know how much we're going to get in. From what I see with my long-range plans, it appears to me that we'll get 3 periods of lecture, which is actually a lot. But in case we don't, I want to make sure that you at least have the bare essentials. And again, I'm going to go over all of this in class, but the bare essentials I want to do for electrolytic, for first galvanic cells. That's probably pretty much all I'll get through today. And then next time we'll do electrolytic cells. And there is a difference between the two. The whole idea of electrochemistry is using electricity or using the movement of electrons, redox reactions, to do work for you. If I put zinc metal in copper, this is what we did in honors. You took a piece of mossy zinc, you put it in copper 2 solution, and if we left it long enough, sometimes it just didn't happen because it just takes too long. But what happens is copper metal forms. Well, for that reaction, you actually see 2 electrons being transferred. 2 from the zinc to the copper. The idea of an electrolytic or of a galvanic or voltaic cell, which we generally call battery, is to separate the 2 components of the reaction. This is called your zinc compartment, and this is your copper compartment. Now, you'd have to understand, too, I didn't really show it here, but these are all in a solution. This would be zinc and the solution would be 1 molar zinc, and let's just say sulfate, which would be the zinc plus 2 and sulfate minus 2 ions. Could be another one, I mean, just same thing here, 1 molar maybe copper 2 sulfate. The idea is it has copper and zinc ions in this cell, copper and zinc and sulfate ions in this cell. So that this cell has a positive and a negative. It has an overall charge of 0 until the reaction actually starts. So this happens, and they don't have to always be set up this way. In this case it is, but not in all cases. What you see is this is called our anode. This is our electrode where oxidation occurs. I like to remember that because the anode starts with an A, which is a vowel. Oxidation starts with an O, also a vowel. So this should be where oxidation takes place. Again, I'm separating the 2 components. The idea is by separating them, I can force the electrons to flow through this external wire. I can then use that movement of electrons to do work. Thus, produce electric charge, run a battery, run a car in some way. But that's what this is instead of losing that energy and just having the reaction occur in one cell, by separating, I can harness the energy through this circuit. So this is my anode. That's where my oxidation occurs. And I can see the same thing, zinc going to zinc plus 2. That's oxidation. Now there's also copper plus 2 going to copper solid. That's reduction. So that my anode is where the oxidation occurs. That's the it should be negative. And the reason we call this negative is because that's where the electrons are generated from. And they move towards the cathode, which is positive. Opposite charges, so it goes negative towards the positive. Now, because the anode, what happens is essentially this zinc solid starts going into zinc ions. That means that this electrode is going to start to deteriorate. This solid starts breaking down. That's why I say it loses mass. Now, at the same time, the cathode is where copper 2 ions are going to copper 2 sulfate. So that this electrode, the copper ions are coming out of solution and they're attaching themselves to this copper metal. So that I should be getting more copper metal on this electrode, so it should gain mass.
At the start of the reaction, would you start with a copper metal?
You usually start with some, yes. And that's what this is. I don't know if you've seen this up here. That's essentially what this reaction is. There's water inside of here, and then there are 2 strips. I believe one is a copper strip and one is a zinc strip. I believe. I'd have to look. I can't remember what the actual electrodes are, but it looks like it from here. And I'm allowing this reaction to take place, and then they're connected with these electrodes. And then I'm harnessing the energy from the electron transfer to run this clock. But yeah, I am starting with some. Now this reaction will eventually stop. Either the usable amount of electrode will run out. Every year I have to take it and actually polish it to get some of the corrosion off. But yeah, this will eventually keep going until at some point the electrodes don't work anymore. So in this case, what you're seeing is the movement of electrons from the anode to the cathode. Therefore, the anode is losing mass, the cathode is gaining mass. Here it has, make sure I got through all this. Now, the problem with this is, you see, as we start to lose mass, you get a buildup of positive charge. Well, that's a problem, because if the charge builds up, the actual cell will shut itself down and nothing will take place. This actually occurs immediately. So the voltage will become zero, no reaction. That's the purpose of the salt bridge. The salt bridge is contains an ion, or a soluble salt. I put potassium nitrate in there. It could be sodium nitrate, sodium chloride. It's just some sort of a soluble salt. A salt that breaks down to the K plus and NO3 minus, or some cation and some anion. The idea is, because this goes into solution, that means that there's a buildup of positive. I need to get rid of that. Meaning the cations are going to move away so that this remains electrically neutral. As I continue to produce zinc plus 2, it will flow this way, the cations. Now they're flowing because, as you look over here, I will also get anions that can move in as well, meaning the nitrate can move in, as long as I can balance out the positive charge, either with negatives or the removal of positive. This becomes a zero overall charge. Same thing here. The copper is coming out of solution, which would leave the sulfate. So because this is negative, you get a movement of cations towards the cathode. These K plus ions, any of the zinc that may have gone in there, they will move into this cell, so that the cell operates with overall zero charge, zero charge. This is a galvanic cell. First done by Galvani. The first battery was by Volta, and then these are named after Galvani, the inventor of these cells. A couple of other things to look at. This is normally how you write the cell. Oxidation, so your anode followed by your cathode. And then the two bars just indicate that a salt bridge is involved. Purpose of the salt bridge then is to maintain the ion balance, or the charge balance, keeping there from a buildup of positives or a buildup of negatives. It allows for the flow of ions, cations toward the cathode, anions toward the anode. Maintains a net overall charge of zero in each cell.
You know how you said like it maintains the charge so that in case like any zinc goes into the cathode and the sulfate, like they all balance each other out. So the fact that the zinc plus 2 ions may come in, like does that affect what happens in the cathode at all, or?
Well, potentially it could, because if you would have zinc plus 2 with the copper, well, let me think. Zinc plus 2, no, because the reaction is non-spontaneous in that direction. So no, I don't see it, because the problem is zinc, being zinc plus 2, does not react with the copper solid or even copper ions. So I do not see that as a possible reaction.
Are there any redox reactions that might have that happen?
It shouldn't, because this is going in the spontaneous direction, so it shouldn't. So again, galvanic cells, after Louis Galvani, the founder of electricity, these work for spontaneous reactions. They are reactions that will occur. Now, if I set this up, someone asked, and we went over this before, what if I set it up in the reverse? What if I set up copper over here and zinc over here? Well, in the reaction, the electrons flow the other way. Essentially, the potential energy of the zinc shell, the zinc cell, is higher than the potential energy in this cell, copper cell. So what happens is it goes from a higher to lower potential energy. It's like a ball rolling downhill. It goes from a higher to lower energy, which means electrons must flow from zinc to copper. No matter how I set this up. Now, one of the things that you want to do with these is often calculate. The question will be, what is the overall EMF of the cell, or the electromotive force? And we often call this its E0 of the cell, which is its cell potential. So it's the difference in electron volts, or the difference in energy of these two cells. So in order to do this, you usually would take the E0 of the cell. Now keeping in mind that that 0 means 1 atmosphere, 25 degrees Celsius, and 1 molar. We've never dealt with the concentration with the standard state before because it really didn't matter. Now it does. Where the E of cell is equal to the E0 of oxidation plus the E0 of reduction. Now, on that, the notes that I gave you, it's on the, let's see if I can find the page here. 1, 2, 3, 4, 5. I think it's page 6. Right? They give you standard reduction potentials, right? So what they do is they take each reaction and they give you what its potential energy is for a reduction. It says standard potential because these are all at 1 atmosphere. Really 1 bar, but very, very close to 1 atmosphere. 1 molar and 25 degrees Celsius. So what we do is we look up each of these reactions. So I look for zinc plus 2 on here, which I don't know if it's on this one or not. Is that on here? Yeah, it is. It's zinc plus 2 electrons goes to zinc solid. Now it's called a reduction potential. The problem is this is the oxidation. So what we have to know is the E0 of reduction is equal to the negative E0 of oxidation, because it's the reverse process. So if it's non-spontaneous in the forward, it's spontaneous in the reverse, and so forth. So what they show me here is that I believe it's negative 0.76, right?
Right.
Now that's if it's reduced. This tells me it's oxidized. So the E0 of oxidation will just be 0.76 volts. Where, in case you're curious, a volt is a joule per coulomb. And then I look up copper plus 2, and that is a reduction, so it's written in the proper form. Isn't that plus 0.34?
Yes.
Okay. So this is positive 0.34 volts. So all I do is I add it. So then what do I do? So when I look at this, it should tell me something. First, that is its cell potential. When E0 is positive, that means that your potential energy of the anode is greater than the cathode. Therefore, the reaction moves in a forward direction. It means the reaction is spontaneous. That's what that tells you. So then it says, okay, calculate the E0, and they give you two other ones to look at here, and I think we have them. I think so. So it says calculate the potentials of the following. So because it's an intrinsic property, it doesn't matter whether the coefficients change. It stays till the E0 value remains the same. So when they show you this, it says the chromate plus 14 plus 6I minus. So they would want to know the E0 of this reaction. So I would look for the chromate, the dichromate. And if you look for it, it's the 1, 2, 3, 4th one down. Is that right?
Right.
Yeah.
And notice it shows dichromate in the reactants. So it just stays as given. It must be reduced. There's no need to go through and look it up and try to figure out what the changes in oxidation numbers. So I know that the reduction of dichromate is what?
Positive
1.33 volts plus. And now I'm going to look up the iodide, right? So it's I minus. So when I look on here,
negative 0.5.
yeah, so now it's, since this is going to be the oxidation, it's just going to be the opposite, negative 0.5. And then I don't know what number you get there. .79 volts.
Yeah.
Again, it's positive, so it tells me that reaction is spontaneous. Okay, so then the other one is aluminum. So when you look at aluminum, it says, so I'm going aluminum to aluminum plus 3.
1.66.
So it's 1.66 volts. Now what this does tell me though, you notice how this is such a really, really big positive number? What that tells me is it is very unlikely that aluminum will gain 3 electrons. It's more likely that aluminum will lose 3.
Right.
Which makes sense because all metals tend to lose electrons. Right? And then it goes to the other one is the I minus again, and that's the negative. Let's see, what's this guy? It's going from I2 to I minus. This time the I2 is being reduced. Now it's
Positive
positive.
0.54.
It's positive 0.54.
Yes.
Wow, now this one's huge. That's like
2.2.
2.20 volts. That's huge.
Mr. Short, please call 5741, Mr. Short, 5741.
Because I want to show you, these aren't all on that sheet. But notice when you go in the back now of that first page, these seem to have a little more meaning than they did before. Because when you look at the back of that first page, I told you that you can use these for metal reactivities. Notice when you look at fluorine, it has the most positive E0. That means that fluorine is the element most likely to be reduced. So that on this list, fluorine is the best. See, so if it's
Electron attractor.
so it's the one that's going to gain electrons the most. So it's the best reducer of anything on here, which means that it is the strongest oxidizing agent, causing something else to lose electrons so it can gain them. Notice which one is the most likely to gain electrons.
Lithium.
Lithium. Even though lithium down here, it has the most negative reduction, so it would have the most positive oxidation. The easiest to oxidize, therefore the greatest reducing agent. So in these notes, you'll see that it says, they give you some things there, and they talk about them, and then it says, which is a stronger reducing agent, F minus, Zn, or I minus. So if I were to do this, I'm going to look at what I have. We'll leave these up here. It's kind of important, I guess. So they give me, which is the strongest, so I better put this in terms of something I know. If it's a reducing agent, it is something that is, it's oxidized. So it better have the most positive E0 of oxidation or the most negative E0 of reduction. And they give me F minus Zn or I minus. So now F minus, in order for it to be oxidized, that's F minus going to F2 plus 2 electrons. The E0 of this,
Negative 28.7.
negative 2.87 volts. Now, what that tells me is this is probably one that's not going to be oxidized. It will more likely be reduced. Now the zinc, if I can find that,
It is
it's like the, so
0.7.
zinc going to zinc plus 2 electrons. That E0 is
0.76.
0.76 volts. I already know this one's out because zinc is better. It's more positive. So that means it's more likely that that reaction will be spontaneous. And then I minus.
Negative 0.5.
Yeah, so you're going to go I minus the E0. So this is going to, there will be two of them just in case to be correct. To I2 plus 2 electrons, negative 0.53, you said?
Yeah.
So it must be zinc. Now they say, okay, using this same idea, essentially we're looking at, can single replacement reactions occur, but not knowing any of those reactivities, just using the chart. So it says, will the following reaction occur? It says, consider a piece of solid lead placed in a solution containing copper 2 ion. You're interested in determining whether or not the lead will reduce the copper into elemental copper and be oxidized to lead 2. So that is for the following reaction. So, will this reaction occur? So for this reaction to occur, lead must go to lead plus 2 electrons. So there must be an E0 of oxidation for lead. We have to find that.
$13, 0.13.
Is it? I haven't found the answer. 0.13 you said?
Yep.
Yep. 0.13 positive, right?
Right.
And then the other one is copper plus 2 electrons going to copper metal. The E0 of reduction there,
0.34.
0.34 you said? Positive?
Yep.
So for this cell, what would be the value?
0.57.
0.47 volts. So when it says, will this reaction occur? Here's the only thing that matters. Is that positive?
Yes.
Does it occur then?
Yes.
Yes. Reaction occur. Okay, so now a solid piece of silver, and chromium 3. So obviously it's going to go to silver plus 1 and then chromium metal. So if that's going to happen, I see Ag going to Ag plus 1 electron as my E0.
Negative 0.8.
Is what?
Negative 0.80.
Negative 0.8.
Right.
Okay. And then I would have chromium plus 3 electrons goes to chromium metal.
0.74.
So
Negative
0.74.
Negative
So
0.74.
it's negative. So what does this mean? I don't even have to add them. You said they're both negative? Is that right? I mean, so the chromium is...
Right. They're both negative.
Yeah.
Yeah.
So they're both negative.
So
My answer has to be negative. That means...
It won't work.
doesn't affect-
Won't work. It won't work. Okay. And that's how numbers 3 and 4 and all the rest of these are done. And you can see there's a whole bunch of them there. They're all the same way. You essentially have to look at what is oxidized, what is reduced. Does the number you get, is it positive for the E0 of the cell? That means spontaneous. Is it negative? The reaction is non-spontaneous. And you can relate this. I mean, you could actually use it to calculate, because you get delta G equals negative N, do this right, F E0 of the cell. When you plug into the expression, what you get is a positive value here, positive value, positive, so that delta G will have to be negative, which means the reaction is spontaneous. So there is a relationship between them. I haven't gotten to that yet, but just in case you're thinking about that, that is true. When you look at, then it talks about reduction potentials, and I do have that right here, so you can see that I could solve for it. The questions, will iron be oxidized to iron plus 2 by treatment of HCl? It's the same idea. So can I take iron to go to iron plus 2 if I add HCl to it? And I could figure out there's 1 electron here, this has 2 electrons, and it's the same idea. I mean, it's really no different. In this case, I'm taking iron to iron plus 2, so
0.44.
0.44. Well, this is 0, isn't it, for hydrogen?
Yes.
Hydrogen is the standard everything is compared to, so it's 0. So it's positive 0.44 volts. So when it says, if I added iron, and will it be oxidized to iron plus 2 by hydrochloric acid? Yeah, of course it will, because the E0 is positive. Next part of this says, well, since they are related, how are they related? Well, delta G and delta and E0 are related through the equation. Delta G is negative MFE. You know that's Gibbs free energy. Negative N. N is the number of electrons transferred. F E0 of the cell. And then F is the Faraday constant. Which is actually on the sheet that you have. And it's 96,500. And we can do it, we'll try to see the best way to do it here. Well, since that's in volts, and this is in, I should probably put it in volts, joules per volt mole. That way the joules, the volts, would cancel out. And then you'd be left with an answer, and the moles would cancel out, so you'd be left with an answer in just joules for delta G. Now the other thing too is, in the last chapter, I made mention of this. At least we talked about it. Right? So that now if delta G is negative RT ln of Kc, then I can say, well, negative RT ln of Kc equals here, negative N F E0 of the cell. I could also solve for the equilibrium constant for this too. Let's see if I wonder if I actually solved it in here. Right out. Let's see. So I guess we could say the ln of Kc equals N F E0 of the cell all over RT. I just got rid of the negatives when I brought that over. And then let's see if I can. I don't think there's a need to. I don't think I need to get on any further. I can't remember if this is on the actual equation, because I don't want to get. But I guess I could solve it from here, because now if I knew N, if I knew F, 96,000, 500. I knew R, 8.314, since it's going to be in joules. T, whatever that is, probably going to be 298. That would be easier to solve. So I could even find the equilibrium constant for this reaction too. So that gets through a lot of this. Now, the one thing that I do have in here is the idea that the E0, this tells me that it's temperature dependent. It also tells me it's concentration dependent, because it's at 1 molar. So now if I look at this, trying to see if I have my... One of the things that I don't think we went into in the last chapter is that we can actually solve delta G at conditions other than standard state. And if I knew what delta G was at the standard state, and I knew what the Kc, negative RT ln of Kc, sorry, left that out. I could now solve for it at whatever set of conditions. Well, it's very similar that we can use this to also solve for E0, because now if I want to know E at any conditions, it's equal to the E0 of the cell. Minus RT over NF ln Q. Because now it's not necessarily at, it's that reaction quotient Q, so it's not necessarily at the equilibrium. Q is equal to the concentration of products raised to the power of X or whatever, I guess Y since it's a product, over the concentration of reactant dx. Now, if you're wondering, trying to see where we have all of these from. Now this is on, it's on the sheet, and I could, I guess, derive it more, and I guess in class it will, but it's more important to know that this is called the Nernst equation. And what it allows us to do is to figure out how does E change when the concentration changes. You see, this is the E. E0 is when it's 1 molar, but what about when it's not 1 molar? And that's essentially what the Nernst equation allows us to do. Now, I should probably have some examples here. Here is, I guess I can't get this now. Here's an example from this. If I told you that Cu plus 2Ce plus 4 goes to Cu plus 2 plus 2Ce plus 3, and the E0 of this cell is 1.36 volts. And I wanted to know, how does E0 change? How does E change, let's say, when the concentration of Ce plus 4 is greater than 1 molar, concentration of Cu plus 2 is greater than 1 molar, concentration of Ce plus 4 is less than 1 molar, and the concentration of Cu plus 2 is less than 1 molar. My one mistake. This is a positive, not a negative. I'm sorry. Bless you. So essentially, what we're looking at is, I'm saying this Q is going to change. When Q changes, how does the E of the cell, how does the E0 change, or the E of the cell change? You can almost think of this in terms of, this is the last thing we'll do, because after this there's really not much. There's just electrolysis reactions, and those are only a few pages. So the next time that people want to meet, if I have different people, I'll just go through this again. If I have the same people, then what I'll do is I will give you some AP style questions with this, and show you how you would answer them. So, the long and short, how do you solve this? Think of it in terms of Le Chatelier's principle. When Q equals Kc, the reaction is at equilibrium. Okay? That we know. When the equilibrium is disturbed, the reaction will shift in order to reestablish an equilibrium. So, think of this when Ce plus 4 is greater than 1. Well, E0 is when it is 1. So what happens when this reactant is greater than 1? It's almost like adding reactant. According to Le Chatelier's principle, when you add reactant, the reaction shifts which way?
Towards products.
Towards the product. So if the reaction shifts towards the products, what does it do?
It becomes more spontaneous.
It becomes more spontaneous. It makes more voltage. So if Ce plus 4 is greater than 1, what is the effect? More voltage. So a higher E value. The number would be greater than 1.3 times 10 to the 6th. How does that change? Well, whatever the number was, you would just put in here, and then you would solve. You would put in the C. Now notice, these are solids. Well, this one is a solid, so it actually wouldn't show up in the reaction, in the Q value. I think I wrote that appropriately. I don't think yeah, there's only one that doesn't show up. So then think of it now in this way. What about when Cu plus 2 is greater than 1? Well, it's almost like adding product. So the reaction shifts that way, which means less spontaneous, which means
Less voltage.
less voltage. How about when Ce plus 4 is less than 1? So now it's almost like removing reactant. The reaction shifts towards reactants, which means less voltage. If Cu plus 2 is less than 1, it's like removing product. Reaction shifts towards the product,
More
more voltage. So essentially, what I've gone through is how to identify a galvanic cell, the parts of it. And you'll see as you go through these practice exams, the first thing they're going to want you to do is be able to label those parts. The second thing is probably some question about the salt bridge, or some question about the gaining of mass, or the anode or cathode. The next question is probably going to be to find the E0 of the cell. It wouldn't be beyond reason to say another question would be something to deal with the change in the concentration. All of those things deal with voltaic cells, galvanic cells, they're one and the same. Reactions that occur spontaneously. The difference is an electrolytic cell is a cell that doesn't occur spontaneously. It is a cell that you have to add energy to. So when we calculate the E0 here, it's how much voltage is given off. When we do the electrolytic cell, it's how much voltage must be added for that reaction to occur. Because it's a cell that does not occur spontaneously. You have to continuously supply it with energy from a battery. So something like breaking down chlorine into, sodium chloride, and making the chloride into chlorine gas. Or it could be making chlorine into hypochlorite. It's you actually adding the energy to do that. That's what we'll do next time, when people come in.
So that one is for only non-spontaneous.
Yeah, electrolytic cells are non-spontaneous reactions. And that's only a few pages in the notes. We've actually gone through most of the notes, almost all. That's almost all of what electrochemistry is. Okay, that's it.